evaluated at a particular value of x. Find the sum of each of the following convergent series. So we're doing 35 here. Nice. You have to first recognize what function it's modeling. So this series is modeling a function at a specific value. What's one observation you can make of the numbers that are involved in this series? What's one specific thing you can notice? They're odd numbers. So what function or what thing do you have that has odd number? Sine. Sine is the one. Do you remember? Okay, so who can tell me right now sine x? What's the Taylor series for sine x? Does it start at x or 1? It starts at x minus 3 factorial plus x to the 5th over minus what? Oh, nice. Okay, excellent. Hey, do we pretty much have it now? Yeah, so this is actually, what is this? This is what? Sine of what? 1. All done. Because what do you get? Plug 1 into this. Let x equal 1. What do you get? That. There it is. That is sine of 1. Do they expect you to know what the value is for the sine of 1? Question. Does that one make sense? Oh, would you like to borrow one?
Yes, please.
I can get you one in a second. Yeah. Any others from the homework? Anything else? Okay, so you're trying to build the general term for this thing right there. Take it piece by piece. Take it piece by piece. Now, what does that? It's going to involve structures that you've seen before. We just have to be very, very careful about how we build it. So let's expand this first. Remember how I like to do that? I like to turn it to follow the same pattern. So what would that be right there? That would be x squared over what? 0 what? Factorial. Okay. So we're dealing with the sum. Let's go from n equals 0 to infinity. And that's a terrible infinity sign. Can someone tell me what the denominator should be? That's relatively straightforward. 2n minus 2? Yeah, sure. So you said this, 2n minus 2 factorial, like that. Does that work? 0. Yeah, it does not quite work. Because when you plug in 0...
Just do it.
Yeah, wait, 2n.
So just do what? I think it's just 2n, right? Like this? Yeah. Start at 0. No, I understand, but I'd like us to come to the agreement that when you have the choice, choose 0 so that we're all starting from the same place so I can keep my sanity and not have to deal with different index values. Like theoretically, could you start this at like 58 if you wanted to? And be like n minus 58? Yeah, you could. It's called having too much free time. I don't know. Okay, we've got it so far. Now though, we have to figure out what the formula is for the numerator. It's going to be x to a certain power, right? Correct? X to some power. When n is 0, what's the power of x? 2. When n is 1, what's the power? 6. When n is 2, what is it? 10. So you remember when we did this in you did that in algebra 1, you had to find like the relationship between the points to find the equation of the line, or maybe it's a quadratic in this case. Is this actually a line? It is. Anybody know what it is? How do you find the slope of a line, everybody? Yeah, rise over y, change in y over change in x. What's the slope of that line? 4. So we know it's going to 4 times n, but is it just 4 times n?
4n plus 2.
4n plus 2. 4n plus 2. Yeah, 4n minus 2. You said 1. Yeah, but 4n plus 2 works. There it is. Does it ask us to do anything else on this? I don't think. Does it?
Negative 1 to the...
And give the starting value of the index. So what's the starting value? 0. It works. We labeled our starting value right there. So does that work is what I'm asking you.
And we need an alternating sign.
Oh, and it's alternating? You're absolutely right. Thank you. So what do we park out here? Negative 1 to the what? To the n. It's actually to the n because the first one's positive and we're starting at 0. So start it. No, it depends on where you start. But so do you now understand more clearly why it drives me crazy if you start at different places? Because you could make a mistake and accidentally have like a +1, or you could be doing it properly, starting at a different index value. Use n's or k's if you really want to. Just let's stay there, okay? Let's just stay there. All of a sudden, Michael starts using like I don't know, t's and starting at 7, and I cry a little bit. Yeah, it says find the radius of convergence for the Taylor series. So how do you find the radius of convergence? What do you have to run?
The ratio.
The ratio test. So you have to run the ratio test on the general form. So the first thing you need is the general form for this, and you don't have to derive it if you remember what the general form is for ln x. We're going to get to that in a second. But if you wanted to derive this, what do you have to do first? You have to list the derivatives and come up with the pattern. Does it work out pretty well?
Yeah.
No, I'm just going to look it up. The general form of this. You find out that ln of x, of 1 minus x, or 28, is going to be, I think it comes out to be negative x minus x squared over 2. Well, I'm sorry, yeah, did I get it wrong?
Oh, no. My
Yeah?
actual question was, I don't know.
To do with the what? Okay, so let me take a look at this for a second. Okay, so when you do the ratio test, do you end up with this right here? Right?
Yeah.
Correct?
Yeah.
So what do you want to do? Oh, do you want to do that limit, or do you want to do a? Can I do the limit? Yeah, sure. So you're doing the limit as n goes to infinity of the nth plus 1 term. So the nth plus 1 term is negative, right? So it's going to be negative x to the n plus 1 over n plus 1, like that.
Okay.
And then it's going to be negative n over x to the n, like that. So what happens when you run this limit? What does this go to? And this, yeah, that goes to 1. And then what does this go to right here? It goes to x. So that's where it comes from. It goes to x. So you know, therefore, what's the radius of convergence going to be? What's the radius of convergence? What? 1. Exactly. Right. Now, does it ask you to actually find the interval of convergence? No, it just asks you for the radius. You don't have to test the endpoints on this.
I don't know what do I do?
How about this? Let's just limit us to the questions it's asking. So the problem here, the endpoints, so you're asking the question, what happens if we wanted to actually do and find the interval of okay, let's try it out here. Let me get some more space. In this interval of convergence, so you're testing, you want to know, do I include the endpoints on this, right? Right? So plug it into the original. So you plug in 1. So when x is equal to 1, when x is equal to 1, what do you get here? Negative 1 minus 1/2 minus what? What do you get? What is that? What, that is the opposite what? Harmonic, right? So what is that? Diverge, right? Then what else can you plug in? Negative 1? If you plug in negative 1, what's going to happen? You end up with 1 minus 1/2 plus 1/3 minus 1/4 plus what? 1/5. And that what? So that what? Converges. Exactly. It was alternating harmonics. So what does it include? There it is. If you did it out. It doesn't include negative 1. It doesn't include negative 1. Make sense? Okay. The theme of what you saw last night was that you can build the Taylor series based on Taylor series that you already know. You can build them. So essentially, it's kind of like what we did when we got to like sand out the -1s to the n power and the absolute value. Like if something looks like what you want, it's probably what you want. It's a new thing in math because usually you have to be more certain than that for it to be useful. But in this case, it works. Here are the 3 things we get to do. We get to substitute sometimes, we get to differentiate sometimes, and we get to integrate sometimes. These are the 3 you have to know. You have to know these things. These 3 you have to, you got it. You got it. If you don't, it's going to be very hard to succeed on this section. What's the easiest one? It begins with a E. So it trains off real nice. It's all positive. All the numbers are there. And then I like going up to cosine next. What's the similarity in sign structure for sine and cosine? Minus, plus, minus. That's right. One of them is cosine is even. Effectively, if you remember E, easy, cosine, even, you should be able to generate all 3 of them, theoretically. It needs to be automatic. It needs to be automatic. It's really important. So a nice straightforward one, if we wanted to generate e to the negative x, where do we take e to the negative x? Yeah, you just plug it into every space where you see the x. Now, in the video, I purpose, in the book, and I did this, which is call it y. Just call it something else, and then what do you let y equal? Negative x squared. So you plug it in all of these spaces. And voila, you now have the Taylor series for e to the negative x. So the nicest one Or the easiest one is just substitution. Because if you just substitute, it's one step.
But
What?
does that like always work?
Yes. But the point is sometimes you might have something that you don't have a close enough relative to work with. This is e to the negative x is super close to something we have the series for. You might get something where it doesn't look directly like something, and then you have to use integration or differentiation or a creative substitution. So for example, this one right here, that one right there looks a lot like one we know the Taylor series for. What does this one look a lot like? 1 over 1. It's like plus y or plus x. You can call it whatever you want. What's the expansion for this? 1 over 1 plus y. Do you remember what it's the really nice one? What is it? What's it start with? Does it start with 1 or x? So it's with that. Yeah. So y plus
y squared plus 1.
Is this what it is? Is that it? Is that it? What do you think? Okay, so that's binomial expansion. I did this example. What did you guys think of this example in the video? If we were okay with sign being in the answer, is this like a 2-second problem? Hold on, yeah. Watch. So yeah, we could say, oh, we know, oh, e to the y is equal to, what is it? What's it start with? 1 plus x, no, y, sorry. 1 plus what?
Y.
Plus y squared. Yeah. Good. So theoretically, if we were okay with sine being in the answer, is this just 2 seconds? Yeah, we could write, okay, e to the what? Sine theta is equal to 1 plus sine theta plus sine theta squared. Oh, yeah. So technically, is this correct? Technically? Technically, this is correct. But what's the thing that we don't really like seeing in there? We don't really like the sine theta in there. We'd love to strip away the sine and just have it in terms of what? Theta. Oh, do we have a way of rewriting sine? What's sine theta equal to? Sine theta is equal to what? X minus
X cubed
over 3,
plus x
3 factorial, plus what?
x
Oh, theta. Hold on. We did theta. We got to have the same. Excuse me. It's going to be theta minus theta cubed over what? Plus theta to the 5 factorial, right? So forth. Oh, so where could we plug that in? This right here, where can it go? There, and there, and there. At that point, what does your mind say?
Dear God,
cancels out.
Dear God, no. Oh God, like, a plus b squared is fine. A plus b cubed, a plus b plus c squared, what about a plus b plus c to the 3rd power? All of a sudden you're like, I don't want to do that, right? Here's the thing. When you're analyzing this, when you start plugging in, when you list a Taylor series, you usually start, you start with the lowest powered things, right? It starts with 1. And then you want, what's the theta term? What's the theta squared term? What's the theta cubed term? Would I have you list this out for like 10 terms? No. I want you theoretically to list out the first 3 and maybe, if you have a lot of time, come up with the general one. Because the problem is, when you plug this in here, you have to square it, right? So let's actually do out the first couple, and I'll show you that it's not that bad. A totally fair question of me would be to ask you, what are the first 3 terms? That's a totally fair question with no sign in it. So what does this look like written out? So we now know that e to the sine theta is going to be equal to 1 plus, instead of sine, what do I write? Ooh, this thing, right? Right? Yay, dot, dot, dot. And then we have the next term, but instead of sine, what do I write? Ooh, this again. You don't like this, right? No. Good. I'm glad that you don't like it, because it'll keep you from doing too much work. Over what? And it keeps going, right? So you're like, man, I have to keep track of too many things. There are too many things for me to keep track of. Actually, if I'm asking you for the first few terms, the first few terms aren't that bad. First of all, are there any other ones anywhere besides that first one? So you know that this thing is definitely going to start with 1. Are there any ones anywhere else? No, there's not. So it has to start with 1. Let's look at the rest of this. What about theta? Theta would be the next term. There's only 1 theta, right? Plus what? So plus theta. Now what's the next term you'd want to find? Are there any theta what? Theta squareds. Are there any theta squareds here? No. Are there any theta squareds here? There are some theta squareds. How many are there? Just one of them, because it's going to be theta times theta. And what's the denominator of the theta squared? 2 factorial. So the first 3 terms are theta squared over 2 factorial. Now, does this keep going? Sure. There's a ton of stuff here, right? Does it keep on going for a long time? But what are the first 3 terms? 1 plus theta squared over 2 factorial. If I asked you for the first 3, you'd be done. Now, it gets a little bit harder because you have to keep track of things. If I want to go to the next term is going to be theta to the 3rd. Well, we have one of them right here. Is there going to be one of them here? No, because when you square it, it's going to be theta squared, theta to the 6th, theta to the 10th. You're also going to have theta to the 8th in there. Is there any way to get theta? Is there any way to get theta cubed out of this thing? No. But what's the next term? Theta cubed. So is there going to be a theta cubed here? So you have to find the theta cubed here and combine it with this one, and you get the next term. Wouldn't be impossible, but could you do that? You could. The point is, this is as far as I could reasonably expect you to go on this, the first 3 terms. It would be totally reasonable to say, find me the Taylor series 3rd degree of e to the sine theta. Clarification, there cannot be sine in the answer. You go, that. Does that kind of make sense? Okay, so at this point, I really want to hammer this here. This one you might think, so you can actually square, if you know 1 over 1 minus x squared, what the expansion is. Because what's the relationship from here to here? This squared is that, right? So you can actually list this and then square both sides, and it does work. It's kind of messy, but you can do it. In the video, though, do you remember what the relationship is? The key to this one is what's another relationship between this and this? The derivative of this is that, right? So if you do the expansion of this, what do? You just take the derivative of both sides. So what does 1 over 1 minus x equal? Do you remember, Fiona? This is the really nice one. What is it? It's x plus what? Exactly. This is the really nice one. But if you differentiate both sides, what do you end up with? 1 over 1 minus x squared. Does everybody see why that's true? Just as a side note. Yeah, because you're doing d dx of 1 minus x to the negative 1. So that's going to be negative 1 minus x to the negative 2 times negative 1. So what happens to the negatives out front? They cancel. I had to do that out just to remember. So you end up with this, but then when you take the derivative of the other side, you get 1 plus, like this. Boom. So what does that mean? Oh, look, we have the answer. What kinds of relationships can you therefore have? We can have direct substitution, we can have differentiation, other times when we do the integration. Yeah. So make sure, I'm not going to do this one out again because it's in the video, but there's a great way to do arctan. When we tried, do you remember I think one of our questions, number 7 from a couple days ago, was list the first few terms of arctan, the Taylor series for it. Why was it kind of hard? Well, yeah, when you took the derivative, what happened? It blew up. Why did it blow up? Because of the chain and product rule. The chain rule kicks out a 2x, and then you start breeding, right? It just keeps on getting bigger and bigger, and that's a problem. In the video, I show you a different way to do it. Make sure you know it. So everybody stand up, find a part of the board, everybody. So up on your board right here, write me the expansion, really pretty for e to the x. Do that for me. Do the expansion for e to the x, please. Negative 1. What's I cubed? Don't do anything yet. Negative I. And what's I to the 4th? 1. And it repeats, right? So let's stare at these things for a second. Do you see a lot of powers of I? Do you see many things that are going to repeat itself eventually in terms of the signs? So for example, let's look at cosine. If you look at cosine, what's the nice thing about all the powers here? They're even, right? The even powers go negative 1, positive 1, negative 1, positive 1. So looking at cosine, it's going to go 1 minus theta squared I squared, right? But what is I squared?
Negative.
Negative 1, so it's negative negative. So this turns into, what does it turn into? 1 plus theta squared over 2 factorial. And this one turns into theta to the 4th over 4 factorial. You get back to negative, but what's to the 6th power going to be? So it's negative negative. So what does it make all of these?
Positive.
Okay, so do you see how we cleaned that up a little bit? We got something a slightly different form. Does everybody see that right there? Slightly different form. Now, theoretically, can you clean up a little bit e to the I theta and sine of I theta? Can you clean them up a little bit? You can. There's certain things you can do. Is it going to be as pretty as this one? Not quite, but is it going to be close? It's going to be close. So this is what I'd like you to do. As an added part to your homework, and class ends in about 2 minutes. Everybody step back from the board for a second. Step back and take a look at this. Are there already some pretty strong structural similarities between cosine, sine, and e? They have denominators with factorials. What do you have here? You have the odd numbers right here. What do you have here? The even numbers. And what do you have right here? All of them, right? I added it to your homework tonight. You have some questions from 10.3 tonight to do for homework tonight, but I added it to your homework. See if you can find a connection between these three. That's your goal. And I'd like you to do it without looking it up on the internet. Investigate the relationship between these three things right here. That's what I would like you to try to find tonight. Okay? Just think about it. There's no like metric. I'm not expecting you to like find it. If you do, by the way, you totally could. It's not impossible. I'm not asking you to solve some unsolvable problem, okay? I'm not setting you up to solve one of like the millennium problems. Okay? This is an awesome thing, but it's just something for you to think about in addition to do your homework, and it's related. It's in the same field of what we're doing. So that's what I want to do. 12:20. You can get out of here.
Well, you got it. I just got it.